All right, let's go ahead and get started. I do want to welcome you back to Unit 10. This is thermochemistry, and you are going to need a calculator for this one, so if you don't have one handy, go ahead and pause the video, and we'll get started. So here we go. We want to talk today about something that's called Hess's law. Hess's law. Hess's law states that whatever mathematical operations are performed on a chemical equation or a reaction, the same mathematical operations are also applied to the heat of reaction, or the delta H. So there's really two parts to Hess's law. First is this. If the coefficients of a chemical equation are all multiplied by a constant, say 2, the delta H is multiplied by the same constant. Okay? So if you double a chemical reaction, then you double the delta H associated with that delta H, with that chemical reaction. So that's the first part of Hess's law. The second part of Hess's law says that if you have two or more equations that you can add up together to obtain an overall reaction, then the heats of these equations are also added up to give you the heat of the overall reaction. Now that's a mouthful to say. I think it's probably easier just to do some problems. So let's just take this example to begin with. For example, for the combustion reaction for propane, we have CH3, CH2, CH3, and that's a gas, reacting with 5O2, combustion means in the presence of oxygen, to yield 3CO2 gas and 4H2O, also a gas. Now obviously the delta H for that is very negative, negative 2044. Now it's virtually impossible to reverse that reaction, but the point is that if we were to reverse the reaction, the delta H would have a sign that's opposite of negative 2044. In other words, positive 2044, right? So delta H then is reversed. The sign is reversed if you reverse the reaction. So that's the first thing. Next one is this. Hess's law allows chemists to measure delta H for several reactions and then to combine the equations and their heats to obtain delta H for a completely different reaction. All right? So if we can combine reactions to form an overall reaction, then we can combine their delta H's to form an overall delta H. So let's take a look at this example. To add the two reactions below, the reactants and products in the two reactions are combined in an overall reaction. So here are the two reactions. We've got N2, which is a gas, plus O2, also a gas, forming 2NO, gas. And then NO, we've also got, so there's a delta H associated with that one. I'll call that delta H sub 1, just like that, okay? So now there's another equation, 2NO, which is a gas, plus O2, which is a gas, forms 2NO2, which is also a gas. That 2 has a delta H associated with it. I'll call that delta H2. Now what if I were to add those two reactions together? Well, I would have N2, which is a gas, plus 2NO, which is a gas, plus 2O2, which is a gas. Those are the reactants. And on the product side, I would have 2NO gas plus 2NO2 gas. But notice NOs cancel on the left and right hand sides of the equation. So two molecules of NO gas are canceled from both the reactant and the product side of the final reaction to obtain the overall reaction of N2 gas plus 2O2 gas yields 2NO2 gas. But the question is, what's the delta H for that? Well, to find the delta H for that reaction, all I have to do is add up the delta H's for the two previous reactions. Since the two reactions were added, their heats of reaction are also added. So now these are the heats of reaction. For the first one, it was a positive 180.5. For the second one, it was a negative 114.1 kilojoules. If I add those up, this is the value that I get, 66.4 kilojoules. So the overall reaction is going to have a delta H then of 66.4 kilojoules. All right? Let's take a look at a slightly more complicated reaction. That's this one right here. It says use Hess's law to determine the enthalpy change for the following reaction. So here's the reaction. We've got 2 sulfurs, solid. This is 2 moles of sulfur, solid, plus 3 moles of O2 gas yields 2 SO3 gas. Now the enthalpies for the following reactions are known. So we know these two delta H's, right? We know the delta H for this reaction, and we know the delta H for the second reaction. Neither one of which is obviously the main reaction that we're interested in, which is this one right here. But what Hess's law tells us is that we can manipulate these equations so that we can get to the overall reaction. So first let's multiply the first reaction by 2 so we can get 2 sulfurs on the reactant side. So notice in the main reaction there's 2 sulfurs on the reactant side, but on this first equation there's only 1 sulfur. So the first thing we're going to want to do is we're going to multiply that first reaction by 2, and there it is right there. So we're going to multiply it by 2. So we're going to say 2 times sulfur, which is a solid, plus O2, which is a gas, yields SO2 gas. Now, remember that the delta H for that was negative 297 kilojoules. But Hess's law states that when you do that, when you multiply by 2, you must also multiply the enthalpy by that same number, 2. So we're going to say 2 times negative 297 kilojoules. The new delta H for that reaction is going to be negative 594 kilojoules of heat. All right, so now let's take a look at this reaction. So now what I have is I have the reverse reaction. I have 2S solid plus 2O2 gas yields 2SO2 gas. Okay, that's the exact reaction that I'm going to need for that first reaction. So now let's deal with the second reaction. Now I want SO3 gas on the right-hand side. The second reaction has it on the left, so I need to flip it. I need to flip that second reaction. So here's the second reaction right here, but the SO3 is on the left, not on the right. So I need to flip it. And by the way, the SO2 is on the right, not on the left, so I need to flip it. So here's what I'll do. I will reverse the sign of the enthalpy, and I get this time negative 198 kilojoules for this flipped reaction, right? So let's go through that again. The second reaction had a delta H of 198 kilojoules of heat, but the reaction needed to be flipped. So when I flip it, I'm going to flip my delta H to a negative 198 kilojoules. So now here are the new reactions together. The first and the second one that have been modified. Remember the first one I doubled, the second one I flipped. Okay? Notice that the SO2 on the left and the SO2 on the right of the reaction will cancel. So these species, this one and this one, are going to cancel away, and I'm left with a final reaction of 2S solid, sulfur solid, plus 3O2 gas yields 2SO3 gas. This is the original reaction. So according to Hess's law, I simply add up the delta H's of these two reactions, the modified reactions. So I'm going to get negative 694 kilojoules plus a negative 198 kilojoules. My total for the net of those two equations is a negative 792 kilojoules. So you see that Hess's law allows me to take two reactions whose delta H's that I do know and modify them to get the delta H of a reaction that I didn't previously know. Okay? All right, I want to talk just a little bit about something called heat of formation. So the reaction we started with was called a formation reaction. Right? Formation reaction. The product was formed from its composite elements, sulfur and oxygen. Right? So if we modify the reaction to give us 1 mole of products by dividing by 2, we get what is known as the heat of formation, right? Which has a symbol delta H sub F. So if I take that initial equation, the one that I started with, which is 2S, 2 sulfur solid plus 3O2 gas, yields 2SO3 gas, and I simply divide everything by 2, because to get the heat of formation I'm going to need a 1 right there. Here's what I get. Sulfur, I'll have a 1 right here, just right there, plus, now I have to have a fraction here, but that's perfectly okay when I'm dealing with heats of formation. So 3 halves O2 gas yields 1 SO3 gas. Now, to get the heat of formation, or delta enthalpy of formation, I'm going to need to divide that delta H that I had previous by 2 because I divided the reaction by 2. So I get a negative 792 divided by 2, and my final heat of formation would be this, a negative 396 kilojoules of heat. And that's what we call the delta H sub F, or the heat of formation. The heat of formation, okay? Very good. All right. Now, the following is for heats of combustion. We're going to be talking about heats of combustion, but I think we'll leave this one for the next video since this is really for AP chemistry students. So I'll see you in the next one. Thanks. Bye-bye.